Okay, our next speaker is Professor Jason Cong from UCLA. Jason is a distinguished Chandler Professor at the CS department, also with a joint appointment from the EE department at UCLA. He has close to 500 publications in different areas, including 13 Best Paper Awards, 3 10-year Most Influential Paper Awards, and the first paper inducted to the FPGA and the Reconfigurable Computing Hall of Fame. He and his former student co-founded Alto ESL, which developed the most widely used high-level synthesis tools for FPGA. He was elected to an IEEE Fellow in 2000, ACM Fellow in 2008, and the National Academy of Engineering in 2017. So today, Jason is going to tell us a little bit more about democratizing customized computing.
Thank you, Sophia. Thanks for the invitation. It's a great workshop. I enjoyed it very much. So coming from a slightly different angle, I admire groups who can do ASIC designs, and Mark and the RISC-V group and many others. At UCLA, we lost that capabilities a number of years ago, so we do only FPGA design. But we do it very frequently in the order of maybe several designs per day. So that's still challenging because you can get multi-million gates designs, and how do we do that? So when we talk about Agile, the hardware design, very quickly people think about high-level synthesis. That was a sort of a dream or vision that came up back in the 1980s. And we are glad that we can be part of that effort. I think Sophia mentioned in 2000, early part of 2000, we had a focused effort trying to enable high-level synthesis to work in a competitive way to RTL designers. And it was quite successful, and we have a software package called XPilot that becomes Auto ESL and acquired by Xilinx in 2011. 6 years later, or 5 years later, Intel also started an effort on high-level synthesis, and with OpenCL first, and then moved to C-based design. So today, you go to Google Scholar, you just Google Vivado HLS or Intel OpenCL, you got the 7,000, 8,000 hits. Basically, there's a large community doing that kind of a design from high level. So what's the problem? But it's not an easy journey, I can tell you, that for people has done high-level synthesis design. How many of you have used high-level synthesis tool? Okay, so if you haven't used it, most likely your students have used it. I can tell you all the kind of challenges that I see my students struggling. Get a first-year students coming in to do acceleration for precision medicine. It's very natural. He started this classical algorithm, Needleman, which for sequencing alignment, right, to compare two sequences. And the nice part is that you take the C code with very little modification, you can get a multi-million gate and the design on FPGAs. So that part is very nice. High-level synthesis works. But if you measure the performance, it's 100x slower than the single-core CPU. So it's, wow, what's the point of doing that? So if you're doing some analysis, you'll find out there's a number of problems. The first problem is that so they have this function, the interface is a char, which means that they were going to read the sequences from the DRAM, 8 bit at a time. So obviously that's very inefficient off-chip communication. And also that there's no concept of cache, because you are designing your own customized processors, right? So they don't buffer it. And you have all these loops that you have, and then each loop, they do a very good job to parallelize, but the amount of loops, they execute it in sequential, right? This is some of the reasons why you get such a poor performance. And then you see a big array, and then that got mapped to a on-chip DRAM. But remember, on-chip DRAM only have 2 ports, and read and write. Obviously, that limits the parallelization you have. So you got to partition it into a number of DRAMs, and then you have to figure out how many way partition is sufficient to maximize the performance. And after all of this struggling, then the senior student comes in and says, yeah, you got to do it this way, this way, this way, and they rewrite the C code. And now, for example, you can do the DRAM buffer, you can do cross-grain pipelining, you can do the overlapping computation with communication, and all these nice things you do, which most of you learn, the most part you learn in a computer architecture class. At the end, so this about the 10, 20 lines of code become 200 lines of code, you indeed get a very competitive architecture, which is about 1,000 times faster now over a single thread CPU. But the effort you spend is that going to this 200 lines of code. And this is also multi-week effort. So this is actually now our second leg of that research, right, after the high-level synthesis effort. I want to see whether I can automate this part. I will call this as like a microarchitecture optimization as much as possible. I don't think you can completely replace a human designer, human being, but that's actually the focus we have. First, we developed a tool initially as a university project called the RASP system. It's all open source, but there's also a company behind that called the Merlin compiler. This compiler uses OpenMP kind of a pragma to drive the hardware design. Remember, OpenMP is very simple. You just say parallel for, and the for loop get parallelized, and or parallel section, and the section of the code parallelized. So they basically give you two pragmas. One is parallel, the other one is pipeline. And if you dig a little bit further, there's a coarse grain parallel, fine grain parallel, and a coarse grain pipeline, fine grain pipeline. And there's also a reduction kind of option there. So from there, the good news is that for the code I showed to you, you basically add in these two lines of a code, the pragmas. One is that you want to do a coarse grain pipelining, and you get a PE engine. You say, so I want to replicate this PE engine 64 times. That pretty much uses up all the resources of the FPGA you have. Boom. On the other hand, you can generate this 200 lines of a messy C code and for high-level synthesis to go there and get a very competitive performance. So that's a first step. I think it's a good success. But then if you think about the first, so this solved the first challenge is that you don't have to do this extensive code restructuring. But then if you think a little bit further is that even you only have two pragmas, but you may actually have 50 lines of code, right? Where do you put these two pragmas? And if you try it exhaustively, there's still that 2 to the 50 combinations, right? Or 3 to the 50, depends how you think about it. So that you need quite a bit of knowledge and experience to do that. So now we are in the phase of seeing whether we can automate this part. So the way we have is actually we're still trying that first we use the machine learning techniques. Actually, we have a reinforced learning-driven techniques to actually tell us, try to do exploration, how do we insert these pragmas in a very efficient way. And the first thing is that we got to define this solution space. You cannot just arbitrarily insert these pragmas. You have to define the valid solution space. We have a way to describe that. In fact, there's a you can actually also directly come in to provide the configurations. And then the second part is that you want to do search in the space. As I said, we tried this multi-arm banded approach and coupled with reinforcement learning. But now our more recent effort is using gradient-based approach coupled with some of our experience with large-scale optimization. I will talk briefly about that. So the objective function we use is actually quite intuitive. We're going to, this is totally discrete, right? But we're still going to use kind of a so-called policy gradient. So when you change from one configuration to another configuration, the latency in terms of number of cycles could be reduced and that could be increased. You compute the delta of that. And you also look at the resource usage in LUTs or BRAMs or the logic or flip-flops. So you compute the ratio of that. Basically tells you, and in the unit of a resource, how much do I improve? So that's the sort of objective function or the guiding principle for us to do the search. There are some challenges is that even you just run the high-level synthesis tool, that it can be quite long, that somewhere between 30 minutes to an hour. The backend place and route is even worse, can be 12 hours to 24 hours. So we have ways to actually address that and through a number of optimization steps. I will not go into the details, but very roughly is that you can partition the design space so you can enable some parallel search. The second thing is that now you find a promising direction, right, that gradients, and how far do you go? So that we actually use adaptive line search techniques, which used quite a bit in some of these mathematical programming optimization. And the solution space can be the complex and the non-linear, non-smooth. So we're using multi-scale optimization to do the search, something we used quite a bit in large-scale circuit placement in the past. In particular, that we actually use mimic a human design process that to analyze the bottlenecks. You don't want to try arbitrarily to insert these programmers. So you do a first round of high-level synthesis. You can get through the Merlin compiler, you can get a very good knowledge about where is the bottleneck of your performance. Then you think about how do you optimize that section, and then you continue to refine that. It's an iterative-based approach. So this actually turned out to be successful, quite successful. Let me show you some result. We have, by the way, everything is tried. These days, it's very easy for you to do FPGA design. Even you don't want to put up a cluster with FPGAs, which we did a number of years ago. We have a cluster, 20 servers, each one with FPGA. Today, you just go to Amazon F1. That's all there. We limited the DSC, the design space exploration, to 4 hours, and with 8-thread CPU to do the exploration. So we tried this Mark suite out of Harvard, I think, and Sophia, you're part of that effort, right? Rodinia, and we actually have now our own customization lab. We looked at AlexNet. So you can see that the design space here is that basically shows how well we are compared to the manual designs. So the manual designs are done by graduate students with a fair amount of effort. So except 2, in many cases, we get within 98, 99% of that. We have good explanations why that there's a couple of designs we are not doing that well. In fact, I want to mention is that I was teaching a class that the CS133 parallel distributed computing. Students actually has a lab making FPGA designs on F1 on for example, 1 layer of CNNs. So we use this tool to come in automatically as a robot to do the design. It actually come out to be the second best performance in a class. So it's not like AlphaGo beating the best Go player, but still it's meaningful compared to that. So that's part of things that are making things easier to do that. But I totally agree with Mark, is that if you want to make things even easier, that a lot of people even don't do C-based designs anymore, that the experts, especially the application experts, they use high-level DSLs. So the question is that can we actually even raise the level of abstraction to get to there to do this? So that's actually in our current research attempt as well. For example, what are some of the popular DSLs people are using in the software domain? Spark is one a lot of people are using. And in the deep learning area, you have Caffe, MXNet, right, TVM, and the TensorFlow. So these are the things we're trying to do. So this is the system we're putting together now at UCLA, that you can start from all of this. And as Mark said, we have to go to an intermediate representation. So in our case, is that because that Merlin C, basically C with a few programmers, works out very well. So that can be 1 layer. But we don't have to be limited to that. I'm also going to talk about the HydroCL language in a few slides later. That's also another layer we can go to. Also, another thing we learned is that there are applications with very clear computation patterns. For that, you don't have to really search randomly, that you can come up with a systematic ways to describe these computation patterns and come up with specialized compilers for that. So the 2 things that we did very well, one is the stencil computation, used a lot in image processing, video processing. The second one is the systolic array. Systolic array used a lot, I think, in deep learning, also in a lot of scientific computing. So these 2, it's all published last year in ASCII-CAD. I will not kind of repeat the result. Where on the other side, for the rest of the patterns, by the way, we're still looking for new patterns. There's another pattern we published last year. We call the CPPs, called the Composable Parallel and the Pipeline Architecture. So it turned out if you have that recursive pattern, we can search very effectively. The key is whether you can predict the performance very effectively so that you don't have to synthesize every time. So that we made a lot of good progress. And then for unmatched patterns, we have to give it to this DSE flow I talked about to do the search. So there's two challenges when you do that. One is that when you go high-level DSL to the FPGA, so you have to make sure you guarantee the semantic equivalence, right? The second part is that you want to make use of the DSL patterns to drive the optimization if possible. So let me tell you two kind of result we have example. One is that we started from Spark code. We made an effort to go to FPGA. There's a lot of people writing Spark code, and this is actually a request coming from one of our big data faculty. He says, can you help us to do that? But there's a challenge. First, Spark code is in Scala and Java, basically. It's all in Java virtual, the machine. So we have to have a kind of a Java compiler and a bytecode to C, and we can get to the right-hand side. Then the other side is what Mark mentioned is that the end-to-end. You have to, this accelerator has to talk to the rest of the Spark code. So that we actually had a runtime system we developed called the Blaze system. That is a Scala-based system. So you can actually interface. We allow multiple, for example, Scala applications to share an accelerator. So that system that we actually worked it out. So there's some encouraging result. We can achieve, for example, somewhere between a few X all the way to 180X speed up on over single-threaded JVM machine. One nice part is that you think about it, you have the map and reduce patterns. These patterns translate very naturally to some of these parallel pipeline architectures. For the ones that where you did not give the hint, we have to use the design space exploration to search for the best combination of that. We did poorly on one is the page rank because the computation is too simple. The other one is the logistic regression. There's a very complex floating point computation on FPGA that was not very efficient. Or others actually were very competitive, and also 80% of performance to the manual designs. So that's actually using a DSL, which is designed for software people, right? So we are also wondering, can we have DSLs more targeted towards hardware developers, hardware designers? So this is actually our second effort is the joint work with Jiru at Cornell, actually on this language called the HydroCL. They got the Best Paper Award at FPGA 19 a few months ago. So the HydroCL actually is heavily influenced by both Halide and the TVM. So as Mark mentioned, one feature we like a lot in the Halide is that they separate the functionality with the scheduling, the optimization. So that's one part of that. But it was not originally developed by hardware designers. So we also add in the customization capability for data types for hardware implementation. For example, various kind of a bit width, memory configurations, right? That was also very important. So this is actually an open source project that we just open sourced this about a month ago. You can download it from this GitHub links. It allows you to have the flexibility to decouple the functionality with the data scheduling, the computation scheduling, data type, and also even the data or computation placement, where should that happen. So with that, actually, that's even more interesting that because you have the DSC in the backend, but then now with the DSL, like HydroCL, it comes with own scheduling function section where you can do some code transformation yourself without rewriting the program. For example, you can apply, we showed you 4 examples, right? Digital recognition is unsupervised learning. Through clustering, there's K-mean, there's a Smith-Waterman for sequencing alignment, there's also convolution. So you can apply the multiple versions with human input. For example, you want to do loop merging, loop reordering, right? You can do loop splitting, and so on and so forth. So in each case, you get translated into new high-level synthesis compatible C, and then we can still search in the back end, figure out how many factor of prioritization, how much pipelining, and how much of a correlation you want to do, and how you partition the memory, and all of those will be taken care of automatically. So by this kind of partitioning, part of that human-directed optimization, part of the machine automated optimization. So I think we're getting very good results. So you can see here it's somewhere between a few X again to 55X improvement on compared to the 8-core CPUs on Amazon. By the way, this is also one way we can hopefully kind of even the playground for comparison. Everything we do now, we just prototype it on F1, so you can hopefully reproduce the result. Okay, so that's what we have. And so I think in summary, that the way you can see we achieve this, I call it democratization of customization by one is the better automation, and then the other one is a higher level abstraction. So this HydroCL project, by the HydroCL, we can use it as a starting point. You can think of a DSL, or can be the intermediate layer. And then we're at the back end, we're adding more and more computation patterns like a stencil, systolic array, CPPs. And then we are also adding this kind of search engine that for you to get the best possible configuration. I think there's, in general, there's a lot of progress. If you look at the ML community, they are also using ML to design the ML models, right? So I think there's a lot to excitement going on there as well. So now our goal is that basically want to enable the domain experts to innovate in algorithm and application space, and that we can automate the rest and compile to specialized hardware. So far, we have been very much focused on the FPGA part. So with that, I think I'll end here. Although I have one more example that I probably put it as a backup slide. Depends whether, do we have time? 30 seconds. Just show you, and again, maybe to repeat the theme about end-to-end optimization. For example, this one of our new research project as part of the CRISP Center, funded by the DoD and SRC, is to look at the near data computation, right? So we're thinking about the FPGA in storage. So this is your storage drive, you have the FPGA there. So it's very challenging. One is that the workload you can accelerate. The other one is how do you even program that? So this is actually a very interesting effort. We introduced this concept of a virtual file read and write. And you can register to the OS, and we have the V file open, virtual file open, virtual file read, so that these virtual functions will make use of these accelerators automatically. So that you do have to change multiple stacks. That we have to change the OS kernel, not OS kernel, but the OS drivers, and the whole host pipeline, and eventually get that. So this is actually something that we're going to report next month. If you're interested, I can talk more later on. It's another way to that added abstraction. For example, you can read the data to get the max or the sum. Obviously, you don't want to read it into CPU to process. So that can be our process, add the FPGA inside the drive or near the drive. Just sort of the new directions. Before I end, I want to thank the NSF, CRISP, and the industry partners for CDAC and our Center for Customizable Domain-Specific Computing, and multiple generations of students, postdocs, and collaborators. Great. Thank you. Yes, Chris.
Most of your focus has been HLS for FPGA, and you mentioned this at the beginning. So could you talk a little bit about what you think the trade-offs are and kind of the promise of HLS for FPGA versus ASICs, and whether there's a role for HLS and ASICs as well?
So the question is about sort of the trade-off between FPGA versus ASIC, especially in case of using HLS. I think actually HLS can be used for both ASIC and FPGAs. You're talking about my own experience that Auto ESL, one was an independent company. It has both ASIC customers and FPGA customers. And then, of course, once Xilinx acquired that, they focus primarily just 100% on FPGAs. I got a phone calls from some executives that's complaining from these ASIC companies saying, how come you even didn't talk to us before company was acquired? So we were quite upset. They were actually moving towards HL space, the design. So I don't think there's a significant barrier. I will talk about one fundamental difference is that for ASIC design, people care a lot about the verification, so that the first-time silicon correctness. So that I still haven't seen a perfect solution yet. For RTL to GDS to RTL to gates, there's formal verification. There's no formal verification from behavior models to RTL, even we use high-level synthesis. So that can be kind of a mental barrier, although we didn't make it worse, right? Think about it, if someone write a C model, you have a whole bunch of engineers converted into RTL modelers, so that's still that gap. The error can still happen, but an automated tool can also introduce errors. So it's always a concern. I don't have a good solution to that. We didn't work on the verification part. FPGA, that concern is minimized to a great extent because you just run it. If it's wrong, and you just reprogram it, right? So that part make people a lot easier to accept. I think we have a talk from NVIDIA. Look forward to hear how do they address this concern, because when we were independent company, you talk to anyone, that the ASIC vendors, that was maybe the second or third question they ask. Once they convinced, okay, you can generate high quality RTL, then so how do we verify then?
Great. Let's thank Jason again.
Okay, thank you.